In cellular respiration, glucose and other organic molecules are broken down in a series of steps to produce energy in the form of ATP. Hi, my name is Ian, and in this video, I will be covering the first and second step of the cellular respiration, which includes glycolysis and acetyl CoA formation. Glycolysis is the part where glucose are broken down into pyruvate in the cytoplasm of a cell, composed of 10 enzyme catalyzed chemical reactions. For every glucose, 2 ATPs are invested, which is then expected to yield 4 ATPs, 2 NADH, 2 pyruvate, and 2 water molecules. There are two major phases in glycolysis, the energy investment phase and the energy payoff phase. And note that at the start, glucose is a 6-carbon compound. In the energy investment phase, the first step is characterized by the conversion of glucose into glucose 6-phosphate with the investment of 1 ATP, which becomes an ADP after going through dephosphorylation. In the second step, glucose 6-phosphate is converted into its isomer fructose 6-phosphate. This chemical reaction is just a simple rearrangement. In the third step, it is converted into fructose 1,6-biphosphate with the investment of another ATP, which again becomes an ADP after dephosphorylation. In the fourth step, fructose 1,6-biphosphate is broken down into two isomer molecules, G3P and DHAP. And note that both of them are now 3-carbon molecules. Between the two isomers, G3P is ultimately the favorite product. Therefore, in the fifth step, DHAP will be converted into the second G3P, which marks the end of the energy investment phase. Moving on to the energy payoff phase, each of the two G3P produced is further converted to produce 2 ATPs, 1 NADH, 1 pyruvate, and 1 water molecule. And as there are 2 G3P, we can expect a total yield of 4 ATPs, 2 NADH, 2 pyruvate, and 2 water molecule per glucose. In the sixth step, G3P is oxidized by NAD+ and converted into 1,3-diphosphoglycerate with the addition of an inorganic phosphate molecule. As a result, the NAD+ electron shuttle is also reduced into NADH, which is to be used in later stages of cellular respiration to produce even more energy. In the seventh step, it is converted into 3-phosphoglycerate, and during this step, an ADP will come to the scene of the reaction to pick up a phosphate to form ATP, conducting a substrate-level phosphorylation. In the eighth step, a simple rearrangement reaction happens as it is converted into 2-phosphoglycerate. In the ninth step, it is converted into phosphoryl pyruvate, which also produces H2O water molecule as a byproduct. In the 10th and last step, phosphoryl pyruvate is converted into pyruvate, which marks the end of glycolysis. During this reaction, ADP also comes to the scene to pick up the last phosphate to form the last ATP, conducting yet another substrate-level phosphorylation. Steps 6 to 10 are repeated for the second G3P, and at the end, there should be a total of 4 ATPs, but 2 net ATP, 2 NADH, 2 pyruvate, and 2 water molecule produced per glucose. On the other hand, pyruvate must be converted to acetyl coenzyme A before the citric acid cycle can begin. First, the 3-carbon pyruvate enters the matrix of the mitochondria and is oxidized, which leads to the release of a CO2 molecule in a process called oxidative decarboxylation. A NAD+ then comes to the scene and picks up an electron, oxidizing the remaining fragments of the pyruvate and also being reduced to NADH. Lastly, the remaining 2 carbon fragments is combined with coenzyme A to form acetyl CoA, which then enters the citric acid cycle.